Hello, this is Christian, and I'm recording a version of the talk I gave at MIT Splash program today. Because there were many excellent questions by students in this talk, I had to go somewhat fast in places and skip some parts of this talk for time. So I wanted to record a somewhat slower, more complete version of the talk for people to refer back to if they wanted to go through something more carefully, or if anyone didn't come to attend the original talk and they wanted to see it anyway. So without further ado, this is the talk I gave on electromagnetism and Einstein relativity. So the goal of this talk is to tell a story about what happens when you nudge an electric charge, when you move a charge around. And to begin our story, I want to have a very simple, down-to-earth, motivating question, no space-time or equations. I just want to ask, when I get in the car and turn on the radio, how does a radio station transmit music to me? How does it send music to me in the car? And the short answer, which will take some time to unpack, is that at the radio station, there's some transmitter. The transmitter is doing some complicated dance where it's shaking electrons around in such a way as to generate radiation, and that radiation is transmitted and picked up by my car antenna. So the upshot is you shake some electrons, and that produces radiation. But I've told you next to nothing because I have not told you what those words mean. So the remainder of this talk will be explaining what precisely those words mean. Okay, and before getting down into the weeds, because eventually we'll have some fairly heavy mathematics, it's always good to start with just looking at some pictures. So I just want to do some very simple pictures for intuition. So to start, we have to remember that like charges repel and unlike charges attract. So what we'll do is visualize the direction that a positive charge would move by drawing a bunch of little arrows. This is called the electric field. So if I put a positive charge in the middle of my kind of coordinate system here or something, the arrows go outwards because if I dropped a positive charge here, it would be repelled because like charges are repelled and it would want to go outwards. But if I put a negative charge smack dab in the middle, all the arrows point in because if I dropped a positive charge here, the positive charge would be attracted because unlike charges are attracted and he wants to go in. So I just fill up space with a bunch of arrows that point in the direction a positive charge would go in. So you just remember, what would a positive charge do? WWPD. So this is what the electric field is for a charge that is sitting still. Now I want to ask the kind of next natural question. What happens if you move a charge? Just nudge it a little bit. So suppose I have an electron, which is negatively charged, so these arrows are pointing inwards, and I nudge it a little bit to the right, and I let go. So I move the electron to a new home, which is sitting right here, and I let go. And in this picture, I've shown the old position of the electron in kind of faded gray. So the only ingredient from physics we need here is something called locality. Locality is telling you that objects in physics, like electric fields or charges or whatever, can only influence nearby objects. You can't instantly have a charge transmit some effect really, really far away to the moon. This is sometimes called spooky action at a distance. There's no spooky action at a distance. You can only affect things nearby. So to affect something far away, it takes time because you have to affect the nearby things, then they affect the nearby things, and it moves outwards. It propagates outwards. So the upshot is that if I have another charge very far away, say it's on the moon, when I nudge this electron, that charge far away cannot instantaneously know that the electric field has changed because the news hasn't gotten there yet. But this means something pretty interesting. So since the electric field can't change immediately, if I'm very far away, so say over here I'm on the moon, there the news that the charge has been nudged hasn't arrived yet. So the electric field arrows have to point to the old location of the charge. They point to the old location before it was nudged. But if I'm very close to the charge, say I'm right here, so there's been time for the news to arrive, so the electric field arrows point to the new location of the charge. So there's two different regions, and if we assume that the electric field is smooth, it can't just jump from pointing one way to pointing another way, there has to be a little in-between region, which stitches them together. So that's this region in the shell. It stitches from the arrows pointing to the old location of the charge to the arrows pointing in the new location of the charge. That stitching is what I mean by radiation. Radiation is a stitching between the old location of the charge, electric field vectors, and the electric field vectors pointing to the new location. That's radiation. So that was the punchline. I just wanted to get this little introduction where we orient ourselves with pictures to understand kind of intuitively what radiation means. So the punchline was that locality means that if I nudge a charge, there's some shell that moves outward and updates the electric field to the new location of the charge. And if that was a little faster, didn't make sense, that's fine. We're going to go through it much more carefully in more detail in the rest of the talk. So here's my plan. We just finished the introduction. Next, I want to tell you at what speed that shell is moving outwards. After that, we're going to dive into some mathematics and understand Maxwell's equations, which are the laws of electromagnetism. Then I'll have a brief little interlude to talk about how real-life antennas work. Then we'll connect with Einstein's theory of relativity and see what this implies about space and time. And at the very end, I have a little epilogue where I'll tell you kind of a cool result about magnetism and try to come back to some bigger picture principles of theoretical physics.